Today we're going to talk about the Van de Graaff generator and charging by conduction. So before you take these notes, go back to Schoology. I've linked a couple of different videos from YouTube that will show you some demonstrations of the Van de Graaff generator. If you don't see those videos, just go ahead into YouTube and type up Van de Graaff generator demos and watch a couple of those videos. They're all pretty much the same. They all pretty much show the same thing. So if you haven't done that, go ahead and do that now. Alright, hopefully you've gone ahead and watched those videos. Let's talk a little bit about how a Van de Graaff generator works. So basically what happens is you're going to see that these are kind of the main parts. And right here we have a wheel, and the wheel is usually turned by electricity. Some of the videos they show how you have a crank, and you could certainly crank this by hand, but it just gets really tiring on your arm. So you crank this, and this wheel and this belt are made of different materials. So through friction, and because of the triboelectric series, the belt gets a charge. And it carries that charge up to another wheel up here, and there's a metal comb that's very close to touching the belt. So the charge basically jumps from the belt onto the metal comb, and then because this metal sphere is touching the metal comb, the charge spreads out around this sphere. And it'll stay there. There'll be a nice big charge build up until the dome is able to discharge. And probably what you saw in the video is somebody either bringing their finger close to the dome, or they brought sometimes a smaller metal sphere next to the dome. And you could see a large shock. So one of the questions we want to ask then is, well, why do you see this shock? And why isn't there a constant flow of charge between your finger or the dome and the Van de Graaff generator? And there's really two reasons for this. One of the reasons is that once the shock occurs, the Van de Graaff is momentarily neutral, and it needs some time to build up a charge. So the Van de Graaff, reason number one, is that the Van de Graaff takes time to recharge. And let me do this a little bit better. Oops. Reason number one is the Van de Graaff generator, and we're going to use VDGG to stand for Van de Graaff generator. The Van de Graaff becomes momentarily neutral after the shock and needs to recharge. The other reason that it doesn't happen continuously is because you're not touching the Van de Graaff generator directly. So what happens, and the reason that the charge is able to go, even though you're not touching the Van de Graaff, is able to go from the sphere of the Van de Graaff to your finger, is because the air around, in between your finger and the Van de Graaff generator, becomes momentarily ionized. And that ionization then allows the charge to go from the Van de Graaff generator to your finger. So the air is briefly ionized, allowing charge to flow. Once the Van de Graaff generator releases the charge, to your finger, the air is no longer ionized. So the Van de Graaff generator, ionized, I think I spelled that wrong. The air is no longer ionized, so the Van de Graaff generator has to recharge so that it can ionize the air again. We'll talk more about that once we start talking about lightning, which is basically operates this in the same way as a Van de Graaff generator. So let's take a look at a couple of things that you may or may not have seen in the video. One of the things that you need to understand about charges is this idea of grounding, or what it means to ground a charged object. Grounding simply means removing excess charge from an object. So removing excess charge from an object. And we do that by connecting the charged object to another, usually much larger object. Electrons are then transferred from the charged object to the ground. And in some cases, the ground can quite literally be the ground that you're standing on, because Earth is an excellent ground. The reason it's an excellent ground is because it has an infinite supply and also an infinite sink of electrons. That means that it can store as many electrons that are needed to neutralize a positive object, and it can accept, just like your sink at home accepts water, it can accept as many electrons as needed to ground an object. So the ground has to be large so that it can store or supply a seemingly infinite amount of electrons. So sometimes you can be ground if there is a small object that is charged, because your body will take those charges as needed. Okay? Now, hopefully in one of the demos you saw either a person's hair standing on end, or in one of the demos they used a wig on the Van De Graaff generator. I saw a demo that used a Barbie doll because her hair was nice and thin and would stand on end. So the question is, why does the person's hair stand on end when they hold their hand on the Van De Graaff generator? Now, the reason is because the person builds up a huge amount of charge. And this charge spreads throughout their whole body. So their hair strands become charged. And they become negatively charged. When this happens, we know that negative objects repel each other. So the hair strands are trying to separate. Just as we see two negative things separate. Okay? Something else that you may or may not have seen on the demos is when we touch another object, a neutral object, for instance, an electroscope, to a Van De Graaff generator. In this case, we are charging the electroscope, and we say that we're charging the electroscope via conduction. This is different than friction. Okay? It's very different from friction. Because if you recall, in friction, one object stripped electrons from another. So for instance, a rubber rod stripped electrons from rabbit fur. And in that case, we end up with two opposite charged objects. So the rabbit fur became positive and the rubber rod became negative. When we charge by conduction, oh, and by the way, this is usually for charging by friction, usually this occurs between two insulators. When we're charging by conduction, we need two conductors. Kind of makes sense, right? Conduction, conductors. We need two conductors. And one doesn't strip electrons from the other. One, the charged object, okay, so the charged object shares extra electrons with the other. So if we have a negatively charged object and a neutral object comes in contact with a negatively charged object, the negatively charged object shares some of its extra electrons with the neutral object, and we end up with two negative objects. What happens if we start with a positively charged object? If we start with a positively charged object, so for instance we have a positive object that's missing a bunch of electrons, that's why it's positively charged, and another neutral object comes next to it, another neutral metal or conductor. Well, that neutral object will share some of its electrons with the positively charged object, and then they will both become positive because there won't be enough of the negatives to cancel out, right? They share, so they'll each be short some electrons, and they will both be positive. So if it starts positive, the neutral shares with the positive, and we end up with two positively charged objects. So that's charging by conduction. Now what you might have seen is a pith ball. So a pith ball is just a small metal ball, and we coat ours, it's graphite, so it's very, very light, and we coat it in aluminum foil. And when it hangs next to the Van de Graaff generator, initially when the Van de Graaff generator and the pith ball are just hanging there, they're both neutral, they're just sitting there. When we turn the Van de Graaff generator on, it becomes negative. Well, the pith ball is still neutral, and we know that a negative object will attract a neutral object. So at first, because we have a negative object and a neutral object, let me do that differently, and a neutral, the pith ball is attracted to the Van de Graaff generator and will move towards it. Because it's very light. But once they touch, then they're both negative. So the pith ball will take on the same charge as the Van de Graaff generator. So the pith ball will become negative. Well, now we have two negative things. We have the Van de Graaff generator, which is negative. We have the pith ball, which is negative. And we know two negatives will repel. So then, very quickly, the pith ball moves away. And if you didn't see that demo, if you search up pith ball and Van de Graaff generator on YouTube, you will see what I'm talking about there. Okay. Another demo that you probably didn't see on the video is when we put, or maybe you did, we put packing peanuts in a plastic beaker. And when we put them in there, the peanuts eventually fly out all over the place. So that should indicate to you that the peanuts pick up a charge. So they become negatively charged. And that means that they're going to repel from the negative Van de Graaff generator. So the question is, how did the peanuts, which are an insulator, so peanuts are an insulator, how did they become negatively charged? Because did they charge by friction? No, they couldn't, because they weren't rubbing against the Van de Graaff generator. So they must have charged by conduction, which is weird because they're insulators. But given a big enough buildup of charge on the Van de Graaff generator, that Van de Graaff is going to be able to push some of that charge through the insulator, just like it's able to ionize the air so that the charge can get from the Van de Graaff generator to your finger. It's able to ionize the plastic cup, and then it's able to charge the peanuts, the packing peanuts, so that they pick up that negative charge. Then they not only repel from the Van de Graaff generator, but they also repel from each other. So the Van de Graaff generator builds up a really strong charge, and that strong charge is able to push its way through both the plastic beaker and the peanuts to charge the peanuts, which are then light enough to push each other away out of the beaker and away from the Van de Graaff generator. Kind of an interesting demo. Work. If you haven't seen a Faraday cage, you should check out, look up a Faraday cage demo on YouTube as well. And you'll see a bunch of different types of demos. But in a lot of times you'll see somebody standing in a metal cage. And then somebody else will bring in a large Van de Graaff generator or a large static electricity device. And you'll see huge sparks going at the cage. And you'll think, oh my gosh, the person standing in that cage is really in danger. They could get shocked, like electrocuted, like from lightning. That's not the case, though. And the reason is that the Faraday cage protects anything that's on the inside from becoming electrocuted or taking on any charge. So a Faraday cage is simply a metal, Faraday cage, simply a metal screen that protects anything that's on the inside from any electrostatic charge. Now the reason it's able to do this is because it's metal. Faraday cage is always made of metal or some kind of a conductor. And conductors have an interesting property. Conductors always keep their extra charge on the outside of the conductor. So conductors always keep any extra charge on the outside of the conductor. So that means that all of the charge from the large Van de Graaff or the large electrostatic device stays on the outside of the cage. So the person or object inside the cage is always perfectly safe. So in class we did a demo where we put a Faraday cage around an electroscope, and we brought the electroscope near the in the cage near the Van de Graaff generator, and the electroscope was not able to pick up any charge or show any charge by moving the leaf. The electroscope didn't show any charge because no charge could get to the inside of the Faraday cage. So since no charge got there, the electrical leaf did not move. This brings us to our next demo. In our next demo, we took the same packing peanuts from before and we put them in a metal coffee tin. And then we put the coffee tin on top of the Van de Graaff generator. And most people would expect the packing peanuts to then fly out of the metal can, because after all, the metal can is a conductor. So the electrons can easily get to the metal can, and people think then that the electrons can easily get to the packing peanuts. But since the metal can is a conductor, the extra charge stays on the outside of the metal can. So the charge never penetrates. And we'll write this down. Charge never gets to the inside of the can, and thus can never charge the packing peanuts. So since the peanuts do not become charged, they don't fly out of the can. Kind of neat. Kind of the opposite of, more than likely, kind of the opposite of what you would suspect. So let's go ahead, kind of last thing here, I think, almost, maybe. Yep, last thing here. Let's go ahead and take a look at what it looks like on a microscopic atomic level on a conductor. So for instance, let's take a look, and let's say we have two metal spheres. And before they contact, we have one that's one that's positive right here, right? Because we got 4 positive things and only 1 negative. And here we have a very negative thing. So let's say these two come into contact. What is that going to look like? So the first thing we have to realize is that the positive things are not going to move. So at the end of the day, each of these is still going to have 4 positive things each. But the negative things are going to move, and they're going to want to share the space equally. So I look here and I say, well, we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total electrons. That means these two spheres are going to share those equally because the electrons like to spread out. So this guy's going to get 6, and this guy's going to get 6. Oops, didn't mean to do that. So now when they separate, again, the positive things will not have moved. And this guy will have 6 electrons. And this guy will, oops, I did that wrong. And this guy will have 6 electrons. So we see that we started with 1 negative thing and 1 positive thing, and we ended up with 2 negative things. So and it happens very quickly. It happens basically instantly. So not like when we had to charge one of the rods and we had to sit there and rub it with rabbit fur for 10 seconds, 15 seconds, whatever. This happens instantly. So as soon as they touch, the electrons move very quickly, and they are shared amongst the 2 objects. That's all I've got for charging by conduction and Van de Graaff generator. I strongly encourage you to watch those demo videos so that you can really see how those interact.